Hello, everybody. There's the usual link to the attendance form and the tutoring appointments that are available. You guys are doing all right. Let's see, let me check one thing here. I do see that Carlson has an exam coming up next week. So something to think about for next week if you guys in his class have questions. I really have no idea what's going on in his class exactly, but if there are things you want to ask about from Carlson's class, feel free. What else do I have here? Lots of things. I have the, let's see here. Teresa, I saw that you had asked a question on Piazza about how to enter the answer for question 3 on the homework.
Yeah.
And I was kind of looking at it, and it does, I mean, it looks, did you figure out how to do it or no?
I figured Dr. Professor Rodriguez, he told me what to do, and it turns out that I just I think I figured out finding the constants correctly. It was just like at the end when you're supposed to write out the formulas.
Sure. Okay.
This is what x1 equals. This is what x2 equals. That's the part that threw me off at the end.
Okay.
Yeah.
It definitely seemed, well, yeah, like, yeah, okay. Okay, I'm glad it worked out. Let's see. Yeah, so, all right. That. Where do I want to start here? So I was planning still on talking more about nonlinear systems of differential equations and kind of the multitude of ways we can look at what the stability looks like around the equilibrium point. And so let me see, I had a place I wanted to start. Yeah, let's look at this. Okay, sure. Let me give myself a little more light in here. It's a little dark. Or I'm just looking at my screen too much and the room is dark compared to how bright my freaking screen is. Okay. Okay. Also, I will point, actually, you know what, let me do this as well. So, it should be surprising to no one, but I'm definitely using Grant's notes to kind of fall off of. So, let me just give you guys a link to the notes that I'm looking at so you can also look at them if you want to. So, the idea with these nonlinear differential equations is we're going to linearize around the equilibrium points. So, and this kind of looks gross. Sorry, one sec. I got all this black dust everywhere. Okay, so let's look at this nonlinear system of differential equations. So this is not the pen I wanted. You the pen I wanted. Yes, you are. So you got dx1 dt equal to x1 times 3 minus x1 minus x2. And dx2 dt equal to x1 minus x2. So clearly nonlinear, right? We have powers of x1 and x2 that are other than 1. Specifically, we have x1 squared in this equation here if we multiply it out. And so what we're going to do is we're going to find the equilibriums just like we usually would, right? We're going to find the equilibrium by setting, well, I should say, we haven't been finding the equilibriums, right? Because we've just been knowing it's 0, 0. The way we find the equilibriums is really virtually the same way we find the critical points for functions of 2 variables. Where we find the values of x1 and x2 where both of these equations are 0 at the same time. just like, before when we had, f of xy equal to something, and we solved the first partial and the second partial equal to 0, right? Same kind of idea. So let's do that. And I'm going to look at, so if I set these equal to 0, this one's easy. I'm just going to make x1 equal to x2. So I know whatever equilibrium points I get, they're going to have to be on the line y equals x, or x1 equals x2. And this one here, I could actually plug in x1 for x2 and write this as, let's see, I don't know. I would probably do it like this. So here's how I'm thinking of this. I'm plugging this in here. And then I would just factor out an x1 from each of these. I've got x1 times 3 minus x1 minus 1. So that means I've got...
James?
Yeah.
I think it's for dx dt, the first line where the arrow is pointing at 0. It's supposed to be x1 parentheses 3 minus x1 parentheses minus x2 for on the right side. Yeah.
Oh, but here's so you're correct, Teresa. But
okay.
I'm trying to find solutions to the system. There are solutions both here and here. So whatever the solution is, x1 has to equal x2. So I'm taking this and then plugging in x1 for x2.
Oh, okay. Sorry about that.
No, you're perfectly fine. It's a good question. And so what's happening here is then I'm solving this, and I'm getting x1 times 2 minus x1 equal to 0. So my solutions are x1 equal to 0 or x1 equal to 2. If x1 is 0, x2 is 0. So I get the point 0, 0. And if x1 is 2, x2 is 2. So I get the point 2, 2. And those are the only points that solve this system and this system at the same time, right? 3, 3 would work here, but 3, 3 doesn't work up here, because if x1 is 3 and x2 is 3, I get 3 times 0 minus 3, which isn't 0. On the other hand, I don't know, 0 for x, no, that's a dumb idea, James. 3 for x and 0 for x2, sorry, 3 for x1 and 0 for x2 would totally work up here, doesn't work down here. So we're finding all the points that are solutions to both of these at the same time. Okay, so yeah. So let's see, what am I doing here? All right. So what we're going to do now is we're going to treat these differential equations like they are functions of two variables, because they are functions of two variables. So let's actually, well, let's go to the other side. So let's say that, dx1 dt equal to x1 times, now let's just multiply it out. It's 3x1 minus x1 squared minus x2, and dx2 dt was, sorry, trying to remember everything, x1 minus x2. And I'm going to call this f of x1, x2, and this g of x1, x2. And then we're going to find the Jacobian matrix. So the Jacobian where we take the partials of this with respect to each variable and the partial of this with respect to each variable. So I'm going to write my Jacobian is going to be, so I'm not going to make sure I write this the right way. Yeah. So it's going to be del f del x1, del f del x2, and then here del g del x1, del g del x2. Okay. And so, well, I'll talk about this in a minute. So finding this here, so I'm just taking the partials, right? So the partial of f with respect to x1 is going to be 3 minus 2x1. The partial of f with respect to x2 is going to be negative 1. Partial of g with respect to x1 is going to be positive 1. And the partial of g with respect to x2 is going to be negative 1. And I guess I kind of want to point out for a second. We really are, I mean, so if you were kind of to, it's hard to say exactly what I want to say here. If you were to kind of think of this function as a surface, right, this f of x1, x2 as some surface in 3 dimensions, we really are actually linearizing that surface, right? We're finding the equation of the tangent line, and the same kind of idea here. So we really are like saying, okay, around this one little point, we're going to treat the surface like it's a plane instead of like a tangent plane, instead of being like some wavy thing. And so the idea here is that now this matrix, well, in fact, let's go ahead and never enough room. So I'll go back to this. So our matrix. So this is the matrix for any point. And what we're going to do is we're going to plug in our different equilibria to see what like the system of equations would look like linearized around that point. So here's what we're doing. Let's plug in 0, 0. So I plug in 0, 0, I'm getting this. I'm getting 3, negative 1, 1, negative 1. I'm going to erase some of this just because it's kind of. Oops. So here's what we're really saying with this. We're saying, use a different color. We're saying near the point 0, 0, our system of equations, our system acts like the system given by these coefficients, meaning the system dx1 dt equals 3x1 minus x2, and then dx2 dt equal to x1 minus x2. And this other kind of x1 squared piece becomes negligible at that point there. And really it's because we're at what derivatives. But what this means for us is then we can do our usual sort of eigenvalue analysis. And we can say, okay, if I find the eigenvalues for this, I can tell what kind of equilibrium point to have, if it's stable, unstable, spiral, whatever. And so what we're going to do here is we're going to find the eigenvalues. So let's see, so I am going to say, I do think the trace determinant method is sometimes a better method, friend. It's just faster than writing out 3 minus lambda times negative 1 minus lambda minus 1 times 1. So I'm going to remind you guys, we can find the eigenvalues are given by trace plus or minus the square root of the trace squared minus 4 times the determinant all over 2. And so in this case, our trace is 2. Our determinant is negative 3 minus negative 1. Negative 3 minus negative 1. And so our eigenvalues are, let's see, negative 2 plus or minus the square root of 4 plus 8 is 12, all over 2. So I know my eigenvalues are real, which means I have to think about the sign. Let's see. Negative 2 minus root 12 is definitely negative. Negative 2 plus root 12 is definitely positive. So my eigenvalues are opposite signs, meaning we have a saddle at 0, 0. And then we can do the same thing for the other critical point, 2, 2. So we're going to go ahead, in fact, let me go ahead and erase here. So if I plug in 2, 2 for x1 and x2. The only thing that's going to be different is this term right here. It's going to be 3 minus 4, which is negative 1. So then what we're saying at this, oh, sorry, 2, 2, not 0, 0. Apologies. Okay. Right, what we're saying is at 2, 2, our system acts like dx1 dt equals negative x1 minus x2, and dx2 dt equals x1 minus x2. That's the linearization near that point. And then we can do the same sort of thing. We can find our eigenvalues. So the lambdas are going to be, let's see. So tau here is negative 2. Also, negative 2 again? No. Oh, sorry. Oh, I made a mistake. It's small, but I made a mistake. I put negative tau here. It's not supposed to be negative tau. It's just supposed to be tau, right? My tau was positive 2, but I mixed and put a negative 2 there. So that should be a positive 2, which still gives us the same result, actually, because we still get a positive eigenvalue 2 plus root 12 and a negative eigenvalue 2 minus root 12. So not too terrible mistake. Okay, over here, our trace is negative 2, and our determinant is 1 minus negative 1, right? Which is also 2. So then our eigenvalues are going to be negative 2 plus or minus the square root of 4 minus 4 times 2 is negative 4 all over 2. So here the eigenvalues are imaginary or complex, and they have a negative real part. So that means it's going to be a stable spiral. Sorry, I'm getting a little crammed here. Let's see again. That's going to be negative 2 plus or minus the square root of 4 minus 8 is negative 4 all over 2. And you could simplify this further, but there's really no need. Right? This simplifies to negative 1 plus or minus I. But in either case, we see they're complex with a negative real part, meaning that we have a stable spiral.
And so, quick question. So, sorry. For the delta and tau, how are you getting those again?
So tau is just the trace, which is the sum of the diagonal elements. So tau is 3 plus negative 1 here, negative 1 plus negative 1 here. And delta is just the determinant, meaning the product of those minus the product of those.
Gotcha. Okay, thank you.
And yeah, I'm going to say more about that today because there is a nice kind of thing to know about them. And there's actually, there's a way to just kind of look at the signs of tau and delta and compare their sizes to know what kind of stuff we have, which I think is maybe worthwhile. So let me see here. Let me just make sure make sure I'm not making some dumb errors. Yeah, cool. Okay. Okay, yeah, there's another. So we'll do this next example in a minute. But so here's what I want to say about this, though. There's actually another way to do this, and this is what's called the graphical method, which I know Rademacher has talked. At least I saw it in his notes somewhere. But actually, before I do that, I want to say one more thing. I do want to ask if this stable spiral is clockwise or counterclockwise. And so here's the thing. I know I said last time or the time before that, you compare these and whichever one is positive tells you which. I couldn't for the life of me tell you which one it was, right? It's just, I'm not going to remember that. I might try really hard, I'm not going to. But you don't have to remember it. Like, there's a really easy way to tell if it's one way or the other. So here's what I've got. I've got this negative 1, negative 1, 1, negative 1. And again, right, this is what we're really saying with this matrix is that dx1 dt is negative x1 minus x2. dx2 dt is positive x1 minus x2. And so if I pick just this note, I should be a little bit careful. No, I don't need to be careful. I might want to pick points that are closer to my actual equilibrium that I'm around, which is 2, 2. Maybe not. I don't know. Yeah, I know. I guess I should because I'm spiraling around 2, 2. So let's see. Okay, here's 2, 2. And 2, 2 should be my equilibrium, right? If I plug in. Sorry, 1 second. Let me make sure I'm not doing something stupid here. 2, 2, right? That's. I need to be a little bit careful here. I want to say you could use. I don't know. I feel like you can just start plugging in points, but I'm not actually sure. So here's my thought. Let me double check something real quick here. All right, I plugged in 2. Why do I feel like I'm doing something, Scott? That's up. Yeah, okay, that's right. 2. Yeah, okay. Sorry, I'm worried I'm making dumb mistakes, and I would like to not make dumb mistakes. So, yeah, okay, that seems right though. So, right, we're kind of imagining this as looking like this. And so if I pick a point like 1, 1, right? To pick a 1, 1, I get -1 minus 1, which is -2. And I get 1 minus 1, which is 0. So at 1, 1, I'm going in the x1 direction. So in the horizontal direction, I'm going negatively. And in this direction, I'm going not up or down. I'm kind of going that way there. And then let's pick another point like, let's pick 2, 2. I know 2, 2 is a bad idea. I think this might not be so great. Maybe I didn't ask a very good question. If I pick 1, 2, so x1 is 1 and x2 is 2. 1 and 2, those are both negative. And if I pick 1 for 2, that's also going to be negative. So I'm going to be going down to the left. This is not making me feel good about this. So here's what I'll say, because I think I blew it. What I will say about this being, I don't know if which way this is spiraling. And maybe we can't know for words for non-linear differential equations. Maybe that's something we just can't know, or at least not for this example. For regular linear ones, we can totally figure it out just by drawing the picture and seeing which way the arrows are going, which is what I was trying to do. Oh well. Okay, but here's what I want to say instead. So actually, what I really want to say is, let's look at p-plane for a second and see how this looks, because it's kind of cool. I mean, I like using the tools I have. So we look at p-plane here. I thought I already had this one up. Let's see. So my equations are x times 3 minus x minus y. That's a y, not a 7. And then we have, what else do we have here? Sorry, x minus y. I suppose I should share my screen so you guys can actually see the things. Sure, I'll have a million windows open. So if we look over here, so 2, 2, right, there's 2, 2. That's one of our equilibrium points. So I'm not gonna, if I click right on it, something funky will probably happen. Okay. But look, 2, 2 definitely looks like the stable spiral we said it was, right? Whereas 0, 0, I think I said was a saddle. So if we get close, right, like if we get too close to 0, 0, so right, here's 0, 0, so I'm getting closer to it, closer to it, closer to it. So it looks like here we're fine, but if we go over on this side of 0, 0, oh, funky things happen. Or this side, right, we start shooting far away from it. So depending on where you are on this side of 0, 0 versus this side of 0, 0, right, you might get pushed far away. If you're over here, you might end up spiraling inwards. So these non-linear differential equations are really kind of different, right? We're less able to kind of tell exactly what's happening everywhere. Okay, so the other thing you can do, which I will warn you ahead of time, I struggle with still. It is always challenging to conceptually think of what's exactly happening, is what's called the graphical method to analyze the equilibrium points. And so let's talk about, so still with the same example. So let's look at our example again. And I'm in, so x1 t equals x1 times 3 minus x1. And not equal to 0, sorry. And again, I'm thinking of this, usually think of the first one, the x1, as our f of, let's do it. And yes, I should stop sharing my screen so you guys can see what I'm writing. And then similarly, dx2 dt equal to x1 minus x2 is g of x1 from x2. And what we're going to kind of do is we're going to find the Jacobian without actually finding the Jacobian at each equilibrium point. So here's what we're going to graph. We're going to graph the nullclines, because the nullclines, where the nullclines intersect, tells us where the equilibrium points are. Now we already know where the equilibrium points are, right? We already know the equilibria are at 0, 0, and at 2, 2. So graphing the nullclines should also show us that. But what I'm trying to say overall is you can use either one of these methods and you don't have to use both. But I want to show you they kind of give you the same stuff. So let's see. So I guess I should use y and x. Oh well. So this is x minus y equals 0. So I get y equal to x is my nullcline. So this is my x2 nullcline. And then here, if I write in terms of y and x, I get x times 3 minus x minus y equals 0. So that's equal to y. So y is equal to 3x minus x squared. It's just a downward opening parabola. It has the point, let's see, if x is 1, I get 2. If x is 2, I get 2 times 1, which is also 2. So it looks kind of like this. Okay. And this is our x1 nullcline. And so here's what you want to remember most of the time. I think this is pretty much always true, but occasionally could not be. Whenever you change sides of a nullcline, you change the sign of your differential equation, right? So over here, my x2 nullcline, or sorry, dx2 dt is either going to be positive or negative, and then over on the other side of it, it'll be the opposite sign. So let's go ahead and find out what it is somewhere. So let's pick a point not on a nullcline. So I don't want to pick 0, 0, or 1, 1, or 2, 2, or anything over here. Let's pick something like 1, 4, and plug it in and just see what happens. So if I plug in, right, here's 1, 4. If I plug in 1 for x1 and 4 for y at x2, so 1, 3 minus 1 minus 4, I get, let's see, 2 minus 4 is negative. So I know that the x1s are negative, or dx1 is negative, and dx2, if I plug in 1, 4, is also negative. Okay. And then here's what I know. So I know both this differential equation and this differential equation are negative over here. And that corresponds to what my graph is showing, right? I know that my arrows are all pointing down and to the left over here. If you look back at the p-plane graph, yes, they point down to the left over here. And then on this side of this x2 nullcline, the x2 or y direction should change. Instead of y going down, now the y's are going to go up. So I'm thinking this like this, where things are going to be going left and up instead of left and down. And so every time you cross one of the nullclines, you're going to change the direction. So right here, instead of being, so I'm crossing the x1 nullcline, so the x1 thing is going to change from negative to positive. Here I'm crossing the y nullcline, so the y things are going to change from positive to negative. Let's see, and we just keep doing it. So where else have I not dealt with here? Down here. So if I go from this region here to this other side, I'm crossing the green x1 nullcline, so the x1 thing is changing from positive to negative. And I think that's all my regions. I've got this, this, this. Right, the red lines don't matter. Those are just our axes. Okay, so now what do we do with this? So we're going to pretend like we're finding the Jacobian by thinking of, oh gosh, there was a cool way of doing this before. And so I'm still trying to find these things. So del f, del x1, del f, del x2, g. I'm still trying to do this. And I'm going to do this at each equilibrium point. So let's look at 2, because it looks like it's a little easier to look at. Okay, so here's what I'm asking for. And this gets a little bit, I feel like a little bit, got to listen at this. And I need to drink of water here. Okay. So I want to know what's happening at this point here. So I'm going to think about traveling in the left to right direction and the up direction. And I want to know, and so these signs here, by the way, right? These signs are the signs of f and g, right? This dx1 dt is what we're calling f. So when I go from left to right, f, right, f, the top thing, goes from being positive to being negative. I'm moving in the, wow, that's an x, by the way. I'm moving in the x1 direction. So I can say at this point, del f, del x1, right, the change in f, as I move in the x1 direction, is from positive to negative, so it's a negative change. And then del f, del x2. So I'm still asking how f is changing, but now I'm asking how f is changing when I move in the x2 direction, which is the y direction. So f goes from being positive to negative. So it's also negative. Okay. Now I'm going to do the same thing for g. So g is the second parts. So when I move in the x1 direction, g goes from being negative to positive. So it's a positive change. And when I go in the x2 direction, g goes from being positive to negative. Okay, so now, this is especially why the tau delta method is maybe preferable, because if you're looking at this, you can be like, oh, hopefully, let's see what we get. We can see that the trace would certainly be negative, right? Because a negative plus a negative is negative. And the determinant would be, let's see, negative minus a, right? This is a positive, or the negative times a negative, minus a negative times a positive, would be a positive. So how does that help us? Yeah, I gotta say more. Let's see, let me think for 1 second here. So here's what we can say for sure. We know the real part's negative, right? Because tau is negative. And no, we can't say that. So we know it's, so the thing about this kind of method is it's not as precise, right? We're not, right? I can't tell, so looking at this, right? I can't tell what to erase, right? So if tau is negative and delta is positive, I can't exactly tell if the discriminant there is positive or negative, right? It's not super easy to know, right? Is tau squared bigger than 4 delta, or is tau squared smaller than 4 delta? And so, right, so if this was true, then we might have other things. But and if this was true, right, if it was less than 4 delta, then this would be negative, and so we know we'd have imaginary, so we know we would have a stable spiral, which is what we actually have there, right? Right? Yeah, we had stable spiral. And then we can, then we can do the same sort of thing, 0, 0. Oh, geez, you threw my pen over me. So we do the same sort of thing over here. We say, all right, so, oh, no, I don't want to do this. I'm running out of room. Sorry. So what someone showed me before, gosh, how did they do this? I know what it is. Gosh, sorry, I have to really make sure I make this make sense. Yeah. Yeah, they drew a right arrow over this first column and a down arrow, or an up arrow, not a down arrow. So no, right. So like when you're looking at these, you're saying, how is f changing as I move to the right? How is f changing when I move up? This one, how is g changing when I move to the right? How is g changing when I move up? So let's look over here, which I know might not be super easy. So over here, if I'm going from this way to this way, I'm starting over here where f is negative, and I'm ending up over here where f is positive. So I have a negative to a positive change, which is a positive change. And then for del f del x2, I'm going from down here to up here. Down here is where f is positive. Up here, f is negative. So it's going positive, negative, negative. And then we do the same thing for g. So from here to here, g is going from negative to positive. From here to here, g is going from positive to negative. So here's what we've got. We've got a trace that is, I don't know, right? Because a positive plus a negative is unclear if it's positive or negative. We don't know the size of things. And then we have a determinant of negative minus negative. Which I know looks silly. Which again, we don't actually know if it's positive or negative. So this is not the most helpful example, right? But that's not the point. The point is you can do this kind of graphical thing and you can kind of see what the signs of the matrix that would be the linearization, the linear approximation of this would be. And while it's not great here, it is great other times. So let's look at another example. Yeah. Sorry, where'd you go with the example? Sure. Okay. Oh, yeah. So there is actually, let me not erase this. Before I do another example, there is something I want to say, because I do think it's worthwhile. Also, let me grab, sorry, let me fix this here. Sure. So let me give you guys the attendance one more time just to make sure. I feel like someone might have come in a little bit later. So there's the attendance again. And then let me also, so I'm going to look at this other thing, which I think is pretty cool. Yeah. Okay. So this is the thing I'm about to be looking at. So we know that, right, we can find the eigenvalues by doing the trace plus or minus tau squared minus 4 delta over t. And now there's some stuff we know, right? We know that the eigenvalues are real if the discriminant, the stuff inside the square root, is positive. I should say really greater than or equal to 0. And, sorry, let me just move things around here. One sec. We also, so which we can kind of rewrite as, how do we like to rewrite this? As delta being less than or equal to tau squared over 4. In a similar way, we know the eigenvalues are complex if tau squared minus 4 delta is less than 0, which ends up looking like tau squared over 4 is less than delta. And so what we like to do is we actually like to kind of draw this picture that defines or kind of categorizes what kind of things we have based on this particular condition. And I believe this graph, well, actually, that's not true. I know this graph is in the old textbook. I imagine this graph is in your textbook, but I didn't look for it, so I don't know where it is. But here's what we're graphing. So we're going to graph the parabola. Let me see. So we're going to call this the tau axis and this the delta axis. And again, remember, tau is the trace. Delta is the determinant. And I'm going to graph the parabola delta equals tau squared over 4. And I guess I could kind of try and graph it nicely. It doesn't really matter that it looks nice. All right. So here's what we know already. If we're above this parabola, right, above this parabola, delta is going to be bigger than tau squared over 4. So up here, where delta is bigger than tau squared over 4, we're going to have spirals because we're going to have complex eigenvalues. So, and the other thing we know is that, right, if the trace is positive, that means the real parts are positive. And so over here in this section, we're going to have unstable spirals. Where the determinant is larger than the trace squared over 4. And over here, we use a different color. We're going to have stable spirals. And now, there's a couple other things. So we've got these 3 sections over here. So, right down here, where the trace is still positive, but now delta is, right, so let's use, I got other colors. And over here, delta is definitely less than tau squared over 4. So then, this part's positive, which means we have real eigenvalues. And so then we have to decide what sign they are. Well, let's see here. So if tau is positive, this part's positive. And then you're adding or subtracting tau squared minus something that's also positive. So what's happening here is this number here is smaller than tau. So if you've got tau minus something that's smaller than it, it's still positive. You've got tau plus something that's positive, it's still positive. So here, they're both positive, meaning over here we have unstable nodes. I'm gonna erase this here. At least let me double check. Yeah, we do. Unstable node. Which makes sense, right? Because again, when you're on the eigenvalues being positive side, or where the trace is positive side, things should be unstable. And then over here, we should have stable nodes for the same sort of reason. Because if tau is negative, but delta is positive, tau squared minus 4 delta will be less, the square delta will be less than tau, and then tau minus something smaller than, or plus something smaller than it won't overcome being negative. Okay, lastly, down here we have our saddles. All right, so what's the point? Well, the point is, if you know this, you can really easily classify what kind of things you've got, right? So for example, I'm just gonna make up something crazy. Let's say we have this matrix, and I'm probably gonna make up something that's not gonna be very interesting just because whatever. Let's say it was 3, 4, 5, -7, right? So the trace is -4. The determinant is negative 21 plus 20, sorry, negative 21 minus 20, which is negative 41. And so we're definitely on the left side over here because our tau is negative. And let's see, tau squared over 4. So tau squared over 4 is going to be 4. And delta is definitely, so we definitely have that delta is less than tau squared over 4, right? So we are definitely down here, right? Well, in fact, I should just say delta is negative, right? And you have to think about that. So I'm negative here, I'm negative here, I'm down in the saddle area over here. So I think it's worth knowing about this because it can kind of be like, oh yeah, I can classify things pretty easily just looking at these two quantities, tau and delta. So worth knowing, actually, so I think this is kind of great actually because here's my biggest takeaway from this right away. If you see that the determinant of a matrix is negative, you got a saddle. It's worth knowing. Okay. Still doesn't help us over here, right? Oh well. Okay, so let's see. So I wanted to do another example. We're kind of short on time, so let's look together at this other example that I wanted to look at. Not you. Hold on, I come back to you. So here is another example, still on that same first, like I said, with the nonlinear autonomous systems of these differential equations. So if we look at this next one here, so here we go, right? I can't highlight. We have dx1 dt equal to x1 minus x1 squared minus x1 times x2, and dx2 dt equal to 3x2 minus x1 x2 minus 2x2 squared. And I'm calling the first one f, I'm calling the second one g. That's always what we're doing. So then we find the equilibrium. And you can, I should say equilibria. And you can find the equilibria graphically by graphing the nullclines and seeing where the opposite ones intersect, right? You can't have an x nullcline intersecting another x nullcline. That doesn't tell you where an equilibrium is. But it's easier here just to do algebraically. So typically when you're trying to solve these things equal to 0, you want to look for something that factors out. So in this first equation, I definitely see an x1 factoring out. So I factor out an x1, and I get x1 equal to 0, or 1 minus x1 minus x2 equal to 0, which I can think of as the equation x plus y equal to 1, or x1 plus x2 equal to 1. Similarly, for this second equation, I can see if an x2 factoring out. So I get x2 equal to 0, or I get 3 equal to x1 plus 2x2, right? Because I get 3 minus x1 minus 2x2 equal to 0. And so then we have to work a little bit to figure out where all the different ways this first equation and the second equation can be 0. So x1 could be 0, and x2 could be 0. 0, 0 is almost always going to be an equilibrium. There are sometimes it's not. But also we could have x1 being 0, and over here, x2 could be 3 halves, right? That would also work, right? Which is the second one here. Or we could have x2 being 0 and plug that in here and get x1 equal to 1. So that's going to give me 1, 0. And then there's always like this, well, not always, but when you have this kind of situation where you have like x1 is a value or there's an equation, and x2 is a value or there's an equation, basically you're getting 4 different combinations. Right? You've got this one and this one, or this one and that one, or this one and this one. And then you have this equation and that equation both being true at the same time. And that's where you actually have to solve the system. So we do like, I mean, you can see the work there probably, but we'd have, I mean, why am I trying to write the thing? It's already there. So, right, we have 1 equal to x1 plus x2 and 3 equal to x1 plus 2x2. We subtract these equations to get 2 equal to x2. So x2 is 2, and then x1 has to be negative 1. And that solves this equation and this equation simultaneously. So there's 4 different equilibria. Then we're going to go down and find the Jacobi matrix, or the Jacobian. So we take all the partials. So we do the partial with respect to f of x1. We get 1 minus 2x1 minus x2. We do the partial of f with respect to x2, and we get negative x1. And then for partial of g with respect to x1, we get negative x2. And then with respect to x2, we get 3 minus x1 minus 4x2, which is all right there. So there's a Jacobi matrix. And then, and then for each equilibrium, we plug those values in for x and y, and then we look at what the matrix looks like for each of those. So for this first one's super easy. So in fact, so I don't even want to look at what he's written here, but I just see, so I've got 1, 0, 0, 3, when I plug in 0, 0, I see my trace is 4, right? My determinant is 3 minus 0. So looking over here where my trace is 4, so I'm on this side of things, my determinant is 3, so I'm somewhere up here. So I do have to actually think about what's bigger. Is the determinant bigger than the trace squared over 4, or is the determinant smaller than the trace squared over 4? Well, let's see. The trace squared over 4 is 4, right? Because it's 4 squared over 4. And the determinant is 3, so I'm definitely down here where the trace is, where the delta is smaller than the trace squared over 4. So I should have an unstable node. And I do. I have an unstable node. So you could either do that, or you could actually go find the eigenvalues. Now here I probably should have just found the eigenvalues because it's super easy, right? They're literally sitting right there for me. Actually, on all of these, except for the last one, pretty straightforward, right? This second one here, when you can just see the eigenvalues, maybe take a hint. It's a good idea just to find them. Here the eigenvalues are -1/2 and -3. So we see it's a stable sink, a stable node or a sink, right? So we'd be over here. For the third one, plugging in 1, 0, we get this matrix where the eigenvalues are opposite signs. So we know we have a saddle. God, the words are challenging today. And finally, this last one we actually have to do a little bit of work for, right? And actually Grant has done it the way that we've been talking about today, where he's using tau and delta. So we plug in -1 and 2. We get this Jacobi matrix, 1, 1, -2, -4. The trace is -3. The determinant is -4 minus -2, which is -2. And when the determinant is negative, you're done, right? You know you're down here in saddle land. Okay. And then there's a picture, right? So actually, we can look at the picture if we want, because I mean, if you got to go, I understand you got to go. If you want to look at this picture for just a minute, let's take a look. So let's see, I've got x minus, but yes, feel free to go if you need to go. I definitely understand life is not just about this class. And then we have 3y minus xy. So if we graph this, let's take a look. And let's make sure I've graphed it right. 3y minus, okay. And so we've got to cut, right, so 0, 0. So let's see actually what we see here, right? So 0, 0, we have an unstable node, which seems sensible, right? If I look at 0, 0 here, right, stuff is definitely taken off away from 0, 0. Okay. If we look at 0, 3/2, which is a stable node or a sink, well, that seems reasonable, right? When I move a little bit away from 0, 0 in that direction towards 0, 3/2, stuff starts pointing in towards it, right? Now, something weird's happening over here, we'll check out in a minute, right? Because we're moving away from that. So it looks like there's probably a saddle over here. Yeah, there is. At 1, 2, sorry, at 1, 0, which is right over here, we definitely have a saddle, right? So we're coming in towards 1, 0, and then we're shooting off in other directions. Yeah, and then finally at -1, 2, we also have a saddle, which is up here, right? So we have, yeah, weird. So again, you're not going to see the behavior everywhere around it because again, we're just linearizing around the equilibrium point. So right locally around that point, you kind of see the behavior you expect to see. But if you start moving too far away from the equilibrium, you don't get it to be like a saddle everywhere or a stable node everywhere. So take it with a grain of salt. All right, you guys, that's all I've got. I posted solutions to the quiz I gave you guys. I think I finished grading them too. They're graded and the quiz and the solutions are posted. So if you have questions about that, feel free to ask. Have a good weekend. We'll see you guys on Monday. For Carlson people, if you have test questions or upcoming questions about your future test, feel free to shoot them my way and I'll see what I can do. I see there's something happening in the chat here. Our sources and nodes. Teresa, so a node, so there's two different kinds of nodes. There's a stable node and an unstable node. A stable node is another word for a sink, and an unstable node is another word for a source. So basically the way you should think about stability, right, is if you're close to your equilibrium but not on it, if you get pushed away from it, you're unstable. And if you get pushed towards it, you're stable. So let me show this, let me graph this again. I'm sorry. Looking at, right, so we had a stable node here at 0, 3 halves. Right, so 0, 3 halves, which is right about here. Right, if I'm close to 0, 3 halves, I get pushed right towards it, right? Whereas 0, 0 was an unstable node. So if I'm close to 0, 0, but not close enough to it, I'm getting pushed away from it. So that's the difference there. Oh, sure, I can send the attendance form again. There you go. That's not the attendance form, sorry. Sorry, blah. It's somewhere here, 1 second. Attendance. There's the attendance form. Okay. Does that clarify the sources and nodes thing? Cool. All right, guys. Take care. Good seeing you.
Thank you.
Always. You're very welcome. Let me see if I can stop this thing. Oh, Cameron. Okay, yeah. Okay.